So one, I'm going to keep reminding you, upload your slides, and I will link them in the program. I know you can't see them there because I haven't refreshed the page recently enough, but they are linked as they come in. Secondly, there are videos for all the previous days linked in the program as well. They are sort of temporary. They're just the raw Zoom recordings. So the room cameras and everything are going to be edited, and I'll replace the links later because the Zoom links also won't last forever. But each block of talks is its own file, so you can also take a look and or share those if you have colleagues who would like to take a look at any talks. Thank you.
All right, well, we're only 7 minutes behind, so I'm going to let Kartheik jump right into our session.
Excellent. Thank you so much. All right. It is, as always, a fantastic pleasure to be here. It really feels like I'm among family doing, the most interesting scientific things that I can imagine and some things that I can't imagine. So I was going to do my usual spiel about Galaxy star formation histories, but I decided, since Mark didn't do the machine learning talk this time, to do, a summary of what's happening in these method development fields that might be broadly applicable to us. So today's talk is about Bayesian inference. Before I jump in, can I just get a show of hands for how many people in this room use Bayesian inference in some way, shape, or form? Okay. Okay, 60 to 70%. How many people use something called simulation-based inference or implicit likelihood or likelihood-free inference? Okay, so this is a much smaller show of hands, which means that this is the right audience. I want to tell you about this stuff. Okay, so let's jump right in. What is statistical inference? So me doing this experiment of collecting data about how many people use inference in their day-to-day life and using that to calibrate my model of whether this talk is useful to you or not is a form of inference. It's wherever you have a model that's defined in some way by some set of parameters, or an underlying distribution, and I'm using observations to update my beliefs about this and learn something about the model in the process. Inference is pretty big in astronomy. Some of the most cited papers in astronomy these days are from people who are developing inference methods like the MC or Multinest, and there have been a rise of conferences that bring people together to talk about methods, ways of doing inference, possible pitfalls, and so on. So why would we care about it at this conference? Well, a lot of the questions that people are posing and asking over here and trying to answer depend on taking observations of our universe and then trying to estimate different properties of interest and using these to inform our models and theories of how galaxies evolve. So whether it's estimating galaxy stellar masses or black hole properties or sizes or halo properties from observations, all of these rely on some kind of underlying data quality assumptions and therefore resulting modeling choices. So for people who haven't been doing inference and want to get into it, or even for people who are just looking for a primer, I've just put together a small list of starting points. These are all either review papers or like polemics that have very strong opinions, both of which can be very useful in sort of like learning about these techniques. And I've started essentially writing a small review paper that summarizes all of this for people who might need it. So you can find a Google Doc with the draft at that link. I welcome contributions. Anyone who wants to help out is more than welcome to. And there's a bunch of packages in Python that are useful, again, as you get started. So the ultimate inference problem, the thing that we're all trying to do here, is essentially learn some kind of physics given observations or given the universe that we live in. Right? This is what we want to get into. The practical inference problem that we end up doing is that we have some set of observations of the universe, and then we have some set of models or theories for the underlying physics that describes this. and we're trying to get, conditioned on observations of the universe, what parts of the model parameter space are consistent. There's a further wrinkle to this by the fact that we have additional steps before we go from a pure model to a model applicable to observations. So that's the P of theta prime given y, and of observations that they are in their infinite signal to noise state, and the kind of observations that we actually deal with, which is the P of theta given y prime. Right? And so what we end up focusing on most of the time in papers tends to be this middle term, which is P of theta prime given y prime. What is the practical model given practical noise constraints, and what can we get from that? If I'm not going to go into the other two terms too much in this talk, but to say that there are being methods developed to deal with that, so if you're interested in that, please talk to me. But focusing on this particular problem, right? So given some set of noisy observations that map to some kind of possibly incomplete model space, we then use Bayes' rule to rewrite this in terms of essentially a likelihood function weighted by a prior, and then try to use our observations to condition this likelihood, and then figure out what estimates of our model parameter space are actually consistent with the universe. Right? So there's a few parts to this. There's the likelihood, the prior, and the evidence. I'm going to speed run through the prior and evidence. So the priors often where our inductive biases about the problem that we are working on come into play. So this is where we put in known physics, known distributions, known assumptions about what we think the universe works like. So this is a very simple example from a fantastic paper by Gwen Edey, where she's looking at how would you get parallax from, or distance measurements from parallax, and it's just showing that how the posterior, the credible region over which your physical distance might change depending on what kind of prior you assume for how distances are distributed. Right. So half the SBI, inference conferences often tend to have talks that focus on like what's the correct prior to assume, and that's a very interesting question. The other part is the evidence, which is the set of, it's the prior probability distribution or the volume over which you're evaluating your likelihood. And the evaluating the evidence given a certain data set and a certain model allows you to actually do model comparisons. So you can actually, this is a plot from a great paper by Alex de la Vega, where he is evaluating different SED fitting assumptions and seeing, given the observations, is there any evidence that says one model is better than the other or not? Right? So that's the prior and the evidence, and I can talk about that more if you have questions, but the main thing everyone tends to focus on is the likelihood. Right? And so the likelihood is basically saying, given some set of model parameters, I can compute, idealized observations for this model, and then compare that to the actual observations and see how good the match is. So given the standard assumption of Gaussian measurement uncertainties, your likelihood essentially becomes the exponentiated version of the chi-squared statistic, right? And so that's where you weight the mean squared error by your model, by your observed uncertainties. If you have correlated noise instead of just plain uncorrelated uncertainties in every band, like you might with spectra, you need to put that into your noise measurements. If you have a weighted mixture of models where you're evaluating the simultaneous likelihood for multiple different factors, you might need to rewrite it as a product of these individual likelihoods. And in astronomy and cosmology, as we go to more and more complex instrumental setups and systems, we end up with these like extremely complex covariances or these extremely large likelihood terms that become increasingly complex to evaluate. Right? So this is the problem that I'm trying to motivate. We solve with different ways of doing inference. The other side of this is that we are getting both better observations in terms of number of objects, but also data quality, and we are getting better method development in adjacent fields of computer science and statistics. And so we really need to find ways to have these sort of talk to each other, especially as we enter this incredible age of millions of objects with incredible statistics for them. And the other part is, as we do these things and as we go to systems that have better signal to noise, we also have to make sure that we understand the noise properties better. So this is a plot from Dan Foreman-Mackey's George package tutorial, which shows that if you're trying to fit this, like it's a mock system, but it's meant to look like a transit with uncorrelated noise, you end up not only getting broader uncertainties, but you actually have a biased estimate for some of the parameters, which if you use correlated noise in your likelihood function, you actually are able to get not only tighter uncertainties, but you are able to get rid of this bias that's being introduced by the noise. So if your system might contain correlated noise, it's really important to include that in your likelihood or forward model. So how is inference getting better? Well, there's two different classes of this. One is just with better samplers and better algorithms. So with things like Hamiltonian Monte Carlo, which Viraj is going to talk about in his talk, or all these new samplers like Peter Beruzzi's ray tracing thing, or something called microcanonical Monte Carlo, you're able to walk through parameter spaces better and therefore reach convergence near your global minimum faster. The other set of advances is these things called likelihood-free inference or simulation-based inference or implicit likelihood inference, depending on who you talk to. But broadly, this used to be a class of these approximate Bayesian computation algorithms where you use some kind of like rejection sampling to figure out what the posterior should look like, close to its truth. But these days, it's become this field where you use a set of neural networks to learn some kind of a joint conditional distribution that makes everything faster. What does this mean? This was a lot of jargon, and I'm sorry. But what it means is these implicit likelihood inference methods often use something called amortized posterior computation, which is where you figure out a way to front load all of your computational cost for inference in some kind of computation that you do ahead of time. So you do it once, and then your inference itself is much faster. You can do this in many different ways, but the crux of it is you usually learn some kind of joint probability distribution between your observations and your model. And because you have now learned this big joint distribution, every time you get an observation, all you do is slice this ND Gaussian along that axis of the observations, and you immediately have a posterior for your model parameter. So instead of sampling, instead of walking around in parameter space like MCMC and trying to find a global minima, this is a much computationally faster algorithm because all you're doing is taking a pre-learned distribution and slicing it. So the way this is done is often to take some kind of complicated forward model. This model can be of arbitrary complexity, but you need to be able to essentially run many, like you sample from your prior, run it through your forward model, make mock observations, and you prepare this set of theta and observations. So model parameters and observations, and then you throw that into all of these fancy neural networks. Essentially, they're either called mixture density networks or masked autoregressive flows or neural spline flows. But you throw it into these networks that essentially learn this joint conditional probability distribution. And once you have learned this paired probability, you essentially then just condition on your observations. And so if we think of it in traditional terms, marginalizing over a distribution is generally much more computationally expensive because you're evaluating a numerical integral, whereas conditioning is just matrix multiplication. So you just have to do it once. And so this makes these algorithms much faster. And I just want to quickly show like two examples. I'm not going to go super deep into these. One is to show what you can do with these methods. So one is you can extend inference to entire populations instead of individual objects now. Earlier, when we wanted to do this, we had to do it in some kind of a hierarchical way where you fit every individual object and then you stack the posteriors somehow. Now what we can do is, so this is one example where we have this model for elasticity in galaxies, and you can model entire populations of galaxies that have some kind of variability built into them. And you can forward model these all the way into observational space. and then use that to perform inference on small populations of galaxies. So this allows you to aggregate signals that might not be readily available in individual galaxies across populations and sample this distribution more efficiently. The other one that I very quickly want to show is how to estimate properties without using summary statistics. So when we talk about galaxy morphology, we often tend to use well-motivated summary statistics like size, concentration, surface, and so on. But what we have been trying to do is essentially with student Juan Alfonso, take the star formation history of a galaxy just from its GRI imaging, and then go back and ask which part of the image did you use to inform your analysis. So this also allows us to do model building to see what features in the galaxy images, not in the summary statistics, it's picking up on to make these kinds of predictions. So this is just one example where I'm showing a clumpy galaxy where it picks out that more flux in the star forming clumps will lead to a higher SFR, and less flux in the bulge will also lead to a higher SFR. And you can take these kinds of things and take an entire population of galaxies and then start coloring them by these importance features to see which parts are important to tell you about some quantity of interest like stellar mass or age or star formation history. We are now extending this to do full inference. So instead of just predicting point estimates, we are getting full posteriors. So this is like the stuff you traditionally get from SED fitting or morphology fitting, except now you're getting both. So these are, to my knowledge, the first joint posteriors on things like SIRSH and T50 or age that come directly from the observations. If I'm wrong, please let me know. But for different kinds of galaxies, it's actually picking out the right features. And sometimes when things are muddled, then it also tends to get confused in the right ways, which is also an important validation. You can also do dust, and then when you get to low signal to noise, you actually see that it's getting more and more uncertain about the objects, as it should. So this is something about posterior coverage and whether or not your model is calibrated properly. You can do all of these tests where you put in random noise and see whether or not it recovers the conjugate prior, as it should. And you can look at which parts of parameter space the model is more uncertain and more certain in its predictions. So one really cute thing that came out of it is very uncertain in predicting the dust for edge on disks, right, as it should be. So to summarize this roughly, there's a lot of potential that all of these models have in terms of being able to fit populations and able to go beyond summary statistics. But there's also a lot of hype where people are told, especially students, are under the impression that sometimes these things work out of the box, or you can learn the priors from the data, or you can do extremely fast sampling in very large dimensional spaces, which is simply not true in most cases. It might be true in some specific cases, but it needs a lot of careful tuning to get to that point. So this is something that we need to be careful about, and I've been putting together this set of validation tests for the community where this might be overkill, but it's at least a set of all the things that I could think of for all sorts of different use cases where a subset of these can be used to build trust in that your method is actually working and doing the thing that it's intended. So I'm going to leave my summary here. Please feel free to go use this document if it's useful to you, and if you want to contribute, I'm more than happy. Simulation-based inference has a lot of potential, and we should carefully try to use it in our problems. Thank you.
All right. Kurt, do you want to plug in, and then maybe while you're setting up, we can take a question? Okay. Sure.
I can stop sharing.
This is really great, Kartheik. This is the best explanation of inference things I've ever seen. I'm particularly interested in SED fitting of AGN. We have a really hard time with this
Right.
fitting individual things. It could take days to weeks even, right? Has anybody, to your knowledge, tried to apply this to broad SED fitting of star-forming galaxies and AGN populations?
So not to both. Yeah. So people have done both individually, as far as I know. The joint one is something that we are sort of laying down frameworks for right now. Chris Lovell and folks at, I guess Sussex are basically putting together this package called Synthesizer that allows you to make the forward model that you would need for doing something like this. So we should talk about it. Yeah. Thank you.
All right, thank you.